Hello, my name is Manoj Kumar. I am going to teach you 4 algorithms. First of all, let's see the Krushkal algorithm. In Krushkal algorithm, we have to first rate the edges and store edges as a list of edges. What is this list consists of? List consists of 2 vertices and takes corresponding weights. Similarly, we will contain all the edges in the list. After that, we have to solve these edges based on the weights. So, these list will contain the edges in the increasing fashion of weights. After that, we have to initialize minimum cost to 0, and we have to take for every edge in the edge list, if those vertex u1, v, vertex 1 and vertex 2 doesn't form the cycle, then we have to update minimum cost to, we have to add the weight to the minimum cost, and finally we have to display the minimum cost. Here, for reading the edge, this takes big of n time because they are n edges, suppose, and then we have for sorting it takes n log n time, and this is big of 1 time, and this for every edge in edge list. What is the length of the edge list? Again n. Big of for every edges this is going to run, so big of n, and that's it. So finally all the algorithm, the final complexity is n log n. Now let us see the time complexity of the primes algorithm. First of all, we will use adjacent list to store this graph, and Fibonacci queues to store the pair of information, weights and vertex, and the weights will be stored in the increasing order, and as well as if there is a time in increasing order of the vertex. First of all, primes algorithm takes the starting vertex. For simplicity, let's assume 0 as starting vertex, and into a pair of information. This is the endpoint which has x and w which has a weight, and it enters a pair of information w of u to the priority key if it is not taken. And afterwards, we will initialize minimum cost to 0, and then primes algorithm greedily selects the pair w and u if the vertex is not taken, and we will add the weight to the minimum cost, and for all the edges u to v and which has a weight w dash, we will enqueue this vertex. If this vertex is not taken, we will enqueue a pair of information w dash to v to the priority queue. This process will run until the priority queue is empty. So the time complexity of this algorithm is, first of all, processing of each edge times time taken to enqueue or dequeue of priority queue. Since we are using Fibonacci queues, dequeue will take log e time, and number of edges will be, in span tree number of edges is v minus 1, that is, let's say e. So the total time complexity is e log e. See the time complexity of the Dijkstra algorithm. For Dijkstra algorithm, first of all, let's take a vector called as distance of size of the vector of vertices, and let us initialize all of them to the infinity. Here there is a carrier, vi means vector and ii means pair of intent, okay? And then for distance of the source to the source itself is 0, and we are going to take the priority queue which holds the pair of the information. The first one will be the distance and second one will be the vertex. So we will first of all push the source to the priority queue, and then this Dijkstra will select the minimum distance which is in the priority queue, and then we are assigning d is the distance and u is the vertex. We will come to this right afterwards. So here you can see for all the edges this will going to run. For all the edges incident from u to v which has w, right? If distance of u plus this weight is less than distance of v, then it is going to relax the edges. We are going to update the distance of the vertex v, and then push the distance and the vertex, this pair of information, to the priority queue. Now let's come to see. Since we are pushing this here, we can have, there will be many more distances with the same vertices. So we are going to deal that here itself. So this is called as lazy division. If the distance is greater, then we are not going to take that. If the distance is less, we are going to take that. Okay, then the time complexity of this is, since there can be many more vertices of the different distance with the same vertices, this is big O of n, and since we are using Fibonacci series, this is big O of log n. In the first glance, it may seem it is log of v squared, but it is not, since we are pruning the search here itself. So the final time complexity will be n log n. In other words, we can say e log e also. At last, we will see the time complexity of Bellman-Ford's algorithm. The main idea of this algorithm is relax e edges v minus 1 times. So let there be an edge, first of all. So, yes, this is the source, and let there be an edge h2 u. If this edge is relaxed, then distance of u will have correct value. So again, if there is an h to u to v, if we relax this edge, and distance of v will have the correct value. So we are going to extend this to all vertices. That means we are going to do this to v times, right? And afterwards, the main idea of, as we said, we are going to do this v minus 1 times. Here is a relaxation for all the vertices, and here v minus 1 time. So the implementation goes like this. First of all, there will be a vector called as distance, and all the vertices will be initialized to infinity. The distance between source to source is 0, and these things. So the first flow, this takes big O of n e time. Why? Spanning tree. So okay, let's say big O of n time, and this takes big O of n time, and this also takes big O of n time. So final complexity big O of n cube, or we can say big O of v cube. The end.